All right, so in this next section, we're going to take a look at 6.2, graphs of exponential functions. So in terms of exponential functions, characteristics here, some base b to the x power. I have a couple of different things that are true. One, b must strictly be greater than 0. It cannot be negative, or we go from real to complex numbers back and forth an infinite number of times, and obviously that causes a problem. And b cannot equal 1, or we just have a linear function. Exponential functions are one-to-one. They do have a horizontal asymptote. Unshifted, it is at y equals 0. Our domain is reals. Our range goes 0 through infinity, non-inclusive. There is no x-intercept. Y-intercept is always at 0, 1 for all of our parent functions. Remember, anything to the 0 power, by definition, always equals 1. So we're always going to have this 0, 1 point. Okay? If b is greater than 1, we are decreasing. And if b is between 0 and 1, or less than 1, obviously keeping in mind that b can't be less than 0, then we have a function that is decreasing. Okay, so here we have two different graphs. The one on the left is where b is greater than 1, and as I go to the right, each unit, I'm multiplying the y value by b. Right, so it's increasing by a multiple of b as I go from left to right. When b is less than 1, I'm still multiplying by that value b, right, as I go from left to right, but it's decreasing because it's smaller. So if I had like 1/2, for example, I could either think I'm multiplying by 1/2 or I'm dividing by 2 every time I go to the right. Okay. So here I just have a couple of different graphs here. There's a lot going on, but really a couple things I want to illustrate. We always have that point 0, 1 for all of the graphs, all the parent functions. But if you look here on the right-hand side of my equation, okay, specifically at these functions where b is greater than 1, notice that as my base grows, I have a function here, 2 to the x, right? 3 to the x is closer to the left of my y-axis to the x-axis. But as I cross over and I pass x equals 0 and I start getting into positive values of x, that function is increasing faster and faster, right? Same thing as that base increases, right? On the left-hand side of the y-axis, I'm hugging the x-axis closer, right? But as I get to the right, it's increasing much, much quicker. It's much, much steeper. Think about it as I'm going from right to left, if I'm going backwards, it's decreasing that much faster, which is why 10 to the x, as it gets to the left of the y-axis, gets closer to the x-axis much, much quicker, right? Because I'm dividing by a factor of 10 each time, not by a factor of maybe 2, okay? Same behaviors happen when b is between 0 and 1, right? The closer it is to 1, the flatter it's going to be. The closer we get to a value of 0, right? Or think about it, here I had 10 to the x. If I had 1/10, I'm going to have a graph that's here, 1 over that b value of 10, okay? So the closer I get to 0, the smaller that fraction is, the steeper the graph becomes in a decreasing fashion. Hopefully that all makes sense. I think it should be pretty intuitive. Sketching exponential functions, right? If we have something very basic, right? Parent function or something with a couple of shifts, we can do that by hand. And we should be able to do that really without a calculator. Here I have 3 to the x, right? There is no vertical or horizontal shift here. So I am going to have a horizontal asymptote. Okay. Let me adjust that just a little bit. Okay. And again, I want to make that dashed, right? That's going to be at the x-axis. Remember all of my parent functions? 3 to the 0 power is 3. 3 to the first power, 3 to the 0 power is 1. 3 to the first power is 3. 3 squared is 9, right? 3 to the third would be 27, so way up off the graph. 3 to the negative first is 1 over 3 to the first, or 1/3. Then we have 1/9. And again, we get so close to the axis, by the time we get to -3, we have 1/27 that I can't really accurately represent that. So at this point, I've got a couple of exact values for my graph. I have my horizontal asymptote, so I can go in and I can sketch a picture of this graph, and it's going to look something about like this. Okay, you can do it in two different colors. You can maybe use the highlighter for the asymptote, but for right now, that's a relatively decent photo, or picture rather, of the graph, right? Next example I have is f of x equals 1/4 to the x. Again, no horizontal, no vertical shifts. So let's do my asymptote with a highlighter. Maybe it'll make it a little easier to differentiate. Okay, so I have my horizontal asymptote at y equals 0, right? Again, I'm going to make this dashed, okay? And then we have 1/4 to the x. So again, I'm starting with the reference point of 0, 1. 1/4 to the 0 is still 1. Now, 1/4 to the first power is, well, 1/4. 1/4 to the second power is going to be 1 over 4 squared, or 1/16. Okay? So I'm dividing by 4 each time as I go to the right. As I go to the left, I'm multiplying by 4. So one thing I can always think is here at 0, 1, I'm going to multiply the y value by 4 when I move one more to the left. So I'm going to be at -1, 4. And at -2, I'm going to be up somewhere 16, maybe somewhere about here. Okay? So again, I have a pretty good representation of what this graph may look like at this point. And I can sketch this graph in here. Maybe it looks something about like this. Okay? If you miss a point, make the point a little bigger. Okay? So here, graph of 1/4 to the x. Right? So let's talk next about graph shifting exponential functions. And before I really get into this, let me throw a disclaimer out there that when we're dealing with graph shifting and exponential functions, when we have basic parent functions or basic left, right, up, and down shifts, this isn't too bad. And what you'll notice is the graph shifting function, there are components here that I typically would list that aren't here. They're not here for a reason. So here I'm saying we have f of x equals b to the x minus h plus k. I completely excluded an a value here. I did that intentionally. As soon as we start having a values that are different than 1, it adds layers of complexity to this. Or if there's some number times x in the exponent, it also adds other layers of complexity to this. And we'll talk about what we're going to do then in a minute. In general, okay, then we're going to have a y or a horizontal asymptote at y equals k. And my locator point is going to go from its original position at 0, 1 to it's going to shift h units left or right, and then k units up or down. So it's going to be at the point h and then k plus 1. All right, so if I have the graph here, f of 4 to the x, I can sketch that parent function. I'm going to do so relatively lightly. And maybe we get a function that looks something about like this with a horizontal asymptote at y equals 0, right? So for 4 to the x, I'm going to have a graph that looks something about like that. Okay. If I want to then graph f of x equals 4 to the x minus 2 plus 3, all right, I'm going to have a horizontal asymptote at y equals positive 3. Again, I'm going to make that dashed. All right. I'm then going to have a locator point that's going to shift 2 to the right and up 3. So if I went from my original locator point here at 0, 1, if I go 2 to the right and up 3, I'm going to be here at 2, 4. Right? Again, that follows my form of h and k plus 1. So at 2, 4, I'm going to have my new locator point. Let me do this in, let's use black. All right. Now, if I take all of my other points and I shift them to the right and up 4, I'm going to have a point here. I'm going to have a point here, so on and so forth as I get closer and closer to the x-axis, and I'll have another point that's maybe somewhere way up here. Right? So I can go through them and I can sketch a picture of this graph. It's maybe going to look something about like this. Again, I've got points here, 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 there, right? And they just kind of get covered up by the line. Okay. Now, I'm going to go through, I'm going to talk about some of the stretches and compressions in the graph and what things are causing different behaviors to occur within the graph. If we have anything that is, and as I mentioned before, anything more than b to the x minus h plus k in terms of graph shifting is probably not your best route. At that stage, you're going to be better off creating an XY table, whether you do it by hand, whether you do it in the graphing calculator, and plotting points that way, right? Main reason, it's going to be more accurate. There are going to be so many moving pieces happening all at once, and graph shifting can be challenging enough as is with the exponential and also with log functions. But once you start throwing some of the other things in there, these become so complex to come up with rules and different things, guidelines to follow so that you can graph it with graph shifting strictly. It becomes a nightmare to keep track of all of it. So once you get to something that's messier, anything more than my example here of, like 4 to the x minus 2 plus 3, I would seriously consider just using an XY table, all right? So some of the other things that can happen with our graphs, right? So let's say we do have an A value. If we have A times B to the X, if A is greater than 1 or has an absolute value greater than 1, it's going to stretch the graph horizontally. It's also going to manipulate and change the distance or the relationship between vertically between your asymptote and your locator point. So it's going to change that y value there as well. It's no longer going to be k plus 1, all right? If it's negative, it flips it upside down and stretches, all right? If it's less than 1 for the absolute value for A, it's going to compress it, all right? It's going to make it shorter and make it flatter, like a pancake, all right? It's going to have a y intercept at 0a, right? And the horizontal asymptote doesn't necessarily change there, but again, instead of it being 1 unit above the asymptote, now it's a units above the asymptote, or possibly below, all right? In terms of reflections, and I don't necessarily like the way this is written in the slide here, so if you had f of x equals negative a times b to the x, okay? Because one thing, b itself can never be negative. This was a little misleading, although order of operations, it's technically correct, but it's misleading. So if I have a negative a value out in front of my base to the power, okay, it's going to reflect our graph over the line y equals x, and it's going to flip it upside down. The second part of this is if I have a negative x in my exponent. I'm absolutely allowed to do that, or to have that. Now think about it. If I had, say, 2 to the x, we know what that looks like. If I have 2 to the negative x, think about my exponent rules. This is equivalent to 2 to the negative first to the x power, right? 2 to the negative first is 1/2, right? So 2 to the negative x is equivalent to 1/2 to the x, and thus I go from 2 to the x, and when I make it 2 to the negative x, it looks like 1/2 to the x. It is a horizontal reflection, okay? And now that graph is decreasing, okay? And hopefully from the exponent rules, and then also from the comparisons of whether b was greater than 0 or greater than 1 or between 0 and 1, hopefully then you're able to put together that comparison in terms of the horizontal reflection to the manipulation of exponents here with these graphs and why it causes a horizontal reflection, right? Again, translations of exponentials, this comes straight out of our book. Feel free to read through all of this, or it's the same fundamental things, but they're just using different letters. I forget what page this is on, but this is a screenshot straight out of our book, where I have, a times b to the x plus c instead of x minus h plus d, all right? It's still doing the exact same thing. Again, they're greatly simplifying all the different things that could be happening. They are not accounting for in this slide, in this graphic, of all the different possibilities that could occur here. Again, which is why I caution you against, if it's anything more than a, and just because for sake of consistency, a times b to the x minus h plus k, right? No sense in changing what we've used all along in the course in terms of values. If it's anything more than a left-right shift or an up-down shift, even if you add in an a value, as soon as you add an a value in, I would be using an XY table. I would not be attempting to graph this with graph shifting. I don't think it's going to work out well. Okay. That's all that I've got in terms of 6.2. All right, it's going to be basically sketching your more basic functions, understanding the different things that are happening in terms of graph shifting, understanding how it changes or manipulates the equation or the outcome of an equation, more so than being able to shift it based on all the different possible moving parts. You should have an understanding of what it's causing to happen. But again, when it gets complex, graph shifting is probably not going to be your best bet. Go to XY tables. Okay? Take a look at these and see if you have any questions, and we will go through that tomorrow. All right, have a good night.